This is the review for the implicit differentiation, logarithmic differentiation, and tangent lines and tangent line approximations. So I'm going to try and cover all that pretty quickly in this video. They're not too difficult once you get the hang of them. So let's start with implicit differentiation. Oh, where's my draw? Implicit differentiation. Not sure if I spelled that right, but you get the point. So there's no way I spelled that right. So what implicit differentiation is first of all, when would it be used? So before, when we were doing explicit differentiation, we'd have something like y equals 3x squared plus 4x, right? Now we can easily differentiate. You get whatever 6x plus 4. Okay. That's explicit, right? And we know that that's the quick and easy way. But think about it. What are you really doing when you're doing that? And if you actually know what you're doing, you can see that you're actually doing a form of implicit differentiation. So what implicit differentiation is how's a good way to explain this? Anytime that you're finding the derivative of y, you're going to write this. Anytime that you're finding the derivative of x, you're going to write this. But if you know anything about fractions, whenever you have the top equal to the bottom here, so we have the top and the bottom equal, right? It's just going to cancel out to 1. So let's go through this and talk about implicit differentiation. So how do we do it? All you have to do is take the derivative of everything in the equation. So we'll start from left to right. So we have y. So what's the derivative of y? Sorry, y. The derivative of y is not y. It would be 1. Right? Because it's y to the first, right? Because it's 1y to the first, this gets multiplied, and then 1 minus 1 equals 0. So it's 1 y to the 0, but y to the 0 is just 1, so you end up with 1. Okay, 1 times, but again, we took the derivative of a y, so we have to use this, times dy over dx. And that's really the whole key to implicit differentiation. Anytime that you're taking the derivative of a y, you just have to multiply that number by dy over dx. Please don't get confused. That's supposed to be a y. It's just very difficult to draw neatly on this. We'll try my best. That's really the whole key. And I don't know how to explain it better than just anytime you take the derivative of a y, you write dy over dx after that number. So then we got to take the derivative of this. So we have 6x, but again, we took the derivative of an x, dx over dx, plus 4, but again, derivative of a x, dx over dx. Okay, so now that we have that, we're going to go with a little cleanup step. And I'm just going to go through and simplify the expressions. So we have 1 times dy over dx. So that's obviously just dy over dx equals 6x times dx over dx. But remember here, since you have the same thing on the top and the bottom, that's just equal to 1. So that's the equivalent of 6x times 1, which can just be 6x. So we're going to do the same thing for the 4 times dx over dx. So that's 4 times 1, it's just 4. So then we see that we got the same answer that we did before when we did it explicitly, because remember that y prime is the equivalent of dy over dx. They both mean derivative of, or derivative is, so the derivative is 6x plus 4 for this equation. So when would you use implicit differentiation? Actually, before I go through that, I just want to hammer it home that the key to implicit differentiation is to write dy over dx or dx over dx anytime that you find the derivative of a variable. If it was z, it would be dz over dx. For now, anything that we do, it's going to be over dx. So dx is always going to be in the denominator. Okay, so when would you use it? Let me just erase this all. The main time that you would have to use implicit differentiation is for a problem like this. Actually, let me rewrite this. Plus times. Okay. So let me change that just to be super sure that nothing's going to cancel out here. Okay. So we have 3y squared plus x cubed equals xy cubed. So we see that we have y's on both sides of the equation. It does not look nice. It's not like the other one where it was y equals whatever. So obviously the key here is that we have to use implicit differentiation. And what implicit can always be a go-to in these cases. If you ever want to just know something, it would be explicit. You can do the least. Implicit, then logarithmic. Right? Implicit can always be used to solve the explicit problems, right? But it can't always be used to solve the logarithmic problems. I'll go through what those are in a minute. But logarithmic can always be used to solve both of these. So if you're ever lacking on your explicit differentiation, you can always just learn how to implicit differentiate. That can be used for any type of problem. So again, what's the key to implicit differentiation? It's the dy over dx and dx over dx. So right now, I just see this and we see we got y's all over the place. I'm just going to implicitly differentiate this. So the key is you're going to start by taking the derivative of each term. So 3y squared, it's going to be 6y. And then since that's a y, it's going to be times dy over dx. Remember, the key to implicit differentiation is if you take the derivative of a y, right? This is a y term. You have to add dy over dx. So then plus 3x squared times dx over dx. Remember, that's an x term, so that's why it's dx over dx. So now what are we going to do here where it's xy cubed? Well, you see that that's actually x times y cubed, and that's just a product rule. So we have our first times the derivative of the second. So that would be 3y squared, but we took the derivative of the second, which was y cubed, right? And since we took the derivative of a y, you have to add dy over dx. Plus the second. We don't need dy here because we didn't take the derivative, we just left it. Times the derivative of x, which is going to be 1, but you have to have that dx over dx because you took the derivative of dx. That's just the whole key. Anytime you take the derivative of a variable, you're going to have to use one of these two, okay? So now, always after that step, make a cleanup step. So we have 6y times dy over dx plus 3x squared times dx over dx, but dx over dx is just 1, so 3x squared equals x times 3y squared times dy out over dx. So I'm going to say 3x y squared times dy over dx plus y cubed times 1 times dx over dx. Remember, dx over dx is just 1, so it's going to be 1 times 1, which just ends up being 1. So we're just going to be left with y cubed over here. So after our cleanup step, what you want to do is you want to try and get the dy terms. You see, we got one here. You want to get them on the same side, and then you can get them alone. So first, you want to get them on the same side. So how do we do that? We can move all the terms away that aren't being multiplied. So I'm going to move this over to the right, and I'm going to move this over to the left. So we're going to be left with 6y times dy over dx minus 3xy squared times dy over dx. Remember, this whole term is being multiplied, so just leave it as one group for now. And then equals, what is this? This is a plus sign here, so it's going to be y cubed minus 3x squared. I'm running out of space here, so I'm just going to leave this up for a second, and then I'm going to erase this. Okay, 3, 2, 1. You can always go back to look at any of that as necessary. Just need room to finish the problem. Okay, so now that we have that, what we can do is we can work to isolate our dy over dx's, which is the goal because we want to find the derivative. So what can we do? We can pull a dy over dx out of each term. So we can do dy over dx times 6y minus 3xy squared. And why are we able to do this? Because if you look down here, this term is being divided by dy over dx, and this term is being divided by being multiplied by dy over dx, right? So any time that you have them, they have a common factor, right? And we can pull out that as a kind of GCF. But in this case, it's not the GCF, it's a common factor that we're pulling out. So we pull that out and we have that equal to the right side. And then finally, we can divide by this term in the parentheses, and we're left with dy over dx equals y cubed minus 3x squared all over 6y minus 3xy squared. And that is our final answer. Remember that dy over dx means the derivative is, right? So now that we have that isolated, we know that that's what we wanted. So we have the derivative is this whole big mess here. And it's okay to get a fraction here. You're actually supposed to get a fraction here. And it's okay to have y's and x's in your answers because remember we had y's and x's all mixed up in the problem. So that's implicit differentiation in a nutshell. The biggest key to remember is that in order to implicitly differentiate, you want to find the derivative of each term, no matter what the variable is. And I'm sorry if you hear my dog in the background. No matter what the variable is, you want to find the derivative of it. And anytime that you take the derivative of a y, you're going to write dy over dx, or you're going to multiply it by dy over dx. And anytime you take the derivative of an x, you're going to multiply by dx over dx. So now we have logarithmic differentiation. Sorry, he's really barking. Logarithmic differentiation. So when would logarithmic differentiation be used? Well, if you have something like y equals x to the x, right? That's when you would use logarithmic differentiation. So if exponent and base have an x, that's when you would use logarithmic differentiation. So we have our term here. So I'm going to go through it step by step. This is the simplest type of logarithmic differentiation that you would have. So step one, before you do any differentiation, what you're going to do is you're going to ln both sides. When I say ln, it's the natural log. So ln of y equals the ln of x to the x. Okay, that's step one. That's always step one in logarithmic differentiation. If you get nothing else out of this, just remember and memorize the steps. Step one, put the natural log in front. Step two, keep that. And then bring whatever the exponent is, in front of the ln. Remember that whenever you have a log and an exponent, the exponent can be multiplied out in front, right? So we bring that exponent out in front, ln of x, right? X times the ln of x. 1 second. Okay, so step two, we have bringing the exponent out in front to multiply it, right? So then step three, you finally want to find the derivative, right? So the derivative of ln is going to be 1 over something, but in this case, it's the ln of y, so it's going to be 1 over y. But what do you have to do? Anytime that you find the derivative of a y, you have to multiply it by dy over dx. So you'll see that there's a little bit of implicit differentiation in here. So then we have to find the derivative of the right side term. So that's actually a product rule because you see that it's x being multiplied by the ln of x, right? So it'll be first times the derivative of the second. So it's going to be 1 over x. But just for argument's sake, I'm going to throw in the dx over dx there. It's going to cross out anyway later because remember dx over dx is just 1. So then plus second ln of x times derivative of the first 1 times dx over dx. Then we do our cleanup step. Let me write it up here. So then step 4, do the cleanup, 1 over y times dy over dx equals, let's see, x times 1 over x plus the ln of x, right? Because this is just 1 times 1, 1. And then we'll actually see that x times 1 over x will drop out, and that just happens to drop out here. It's not always going to drop out because remember, that's going to leave you with x over x, which is just going to be 1, right? So we are going to have our 1 over y times dy over dx equals 1 plus the ln of x. So then we can do step 5. And then step 5 in any logarithmic differentiation is you're going to take this 1 over y and you're going to multiply, or you're going to, I guess, divide by 1 over y, but that's the equivalent of multiplying by y, right? That's just a keep, change, flip rule, right? So then you're going to be left with dy over dx equals y times 1 plus the ln of x. Okay. Step 5 is just you're taking this and you're multiplying y times every term on this right side. Okay. Just give me a second here. Just make sure that I cover that all. I believe I did. Whatever. I think I did all the steps right there. Even if I did the arithmetic wrong, the steps are still going to be the same. Then that's going to be your final answer. So those 5 steps. Okay. 1, put the ln in front. 2, bring the exponent in front of the ln. 3, you find the derivative of each of them. Right. Remember to keep the dy over dx. That's key for everything. 4, just clean up. 5, you want to multiply the y to the other side, okay? And that can be done no matter what. Even if in the exponent, it says like if it says y equals x raised to the cosine of x or anything like that, anything like that, it's the same steps. You're just going to put the ln in front of the x raised to the whatever, and then you're just going to bring the exponent out in front of the ln. And that's how you clear up that issue. Okay, that's the key to logarithmic differentiation. Okay, it can get a little bit more challenging when you have something like y equals x raised to the cosine of x, right? I'm just going to go through this one quick. ln of y equals the cosine of x times the ln of x. I just did that all in one step. Remember, I just did the ln, then brought this out in front, right? So then we take the derivative of this 1 over y times dy over dx equals, this is a product rule. So we have the first times the derivative of the second 1 over x times dx over dx. I'm just going to cancel this out now because I know that's 1. Plus the second ln of x times the derivative of the first negative sine of x, right? Times dx over dx. Again, though, that's just going to be 1, so I'm going to cancel that out. Clean it up a little bit. 1 over y times dy over dx equals the cosine of x times 1 over x plus the ln of x times the negative sine of x, right? So now we get to our final step, and we're just going to multiply the y over to the other side. dy over dx equals y times the cosine of x times 1 over x plus ln of x times the negative sine of x. I know I went through that quick, but really I'm just using the same exact steps that I did before. I went through them a little quick, so you can always pause, go back, whatever you need to do. Once you've memorized those 5 original steps, you can really apply it to any question, and it'll fit. It's the same thing for anything during this unit. If you understand how to plug into the original, let's say, expression or rule, then you can use that in any circumstance. Now we're going to go on to tangent line approximations. Some people find this is the hardest part of the unit. Once you understand how to do it, it's not too difficult. The couple keys to this. One is this equation. Memorize it, do whatever you have to do, engrave it into your memory. This is your point slope form. And just like y equals mx plus b, it's just a way of writing a line. Except with this, you don't actually need the y-intercept. You can just use any, wow, look at that, a point and the slope, and you can plug it into the equation. So that actually kind of segments me into the next part of the tangent lines. So I'm just going to write the topic here. Tangent lines. So we have tangent lines, okay? In order to find a tangent line, you need 2 things, the point and a slope. Kind of given away by this name here, point slope form, okay? And I can't emphasize this enough. In order to do any of these problems, you have to memorize this equation. Y minus y1 equals m times x minus x1. Y minus y1 equals m times x minus x1. Okay, not a slop, it's a slope, okay? So let's say we have a question like this. Y equals 3x to the third plus 2x. And we want to find the tangent line when x equals 2. So how are we going to do it? Well, first off, we're going to find a point, right? So how do we find a point? What we can do is we can just take this x value and plug it into the equation. So we get y equals 3 times 2 cubed plus 2 times 2. Y equals 3 times 8 plus 4. Y equals 24 plus 4 equals 28. All right, so our point is 228. That's simple. So step 1, take whatever the x value is and you plug it in to find whatever the point you need to use. Step 2, we got to find the slope. The slope's a little bit more difficult, But if you remember, what is the slope? The slope is the derivative. The derivative is the slope of the tangent line, the general equation for the slope of the tangent line anywhere along curve. The general equation, right? But now that we have a point, it's no longer the general equation, it's the slope of the tangent line at x equals 2, right? So we're going to follow, or we're going to find the derivative for this, right? So the derivative equals, let's see, 9x squared plus 2, right? That's our derivative. So then all we have to do is we have to plug in x equals 2 to the derivative. So then y prime equals 9 times 2 y prime equals 9 times 4 plus 2. 36 plus 2 equals 38. Pretty sure it's 38, right? So our slope here would be 38. Okay, simple enough. So step one, whenever you have the tangent lines, is you want to find the point, and you do that by plugging in the x value into the original equation. That's algebra 1. And then in order to find the slope, which is the next step, you have to find the derivative, which the derivative is the general equation, but then you can plug in x equals 2 to find the tangent line at that specific point, right? The slope of the tangent line at that specific point. So you plug x equals 2 into whatever your derivative is, and that's how you find the slope. So now once you have your point and your slope, you can go back to this equation, y minus y1 equals m times x minus x1, and you can plug in y minus 28, remember, because this would be y1, this is x1, and then this is our slope. Slope would be m. Y minus y1 equals the slope times x minus 2. And that is the equation. If you want to feel special, you can rewrite it. Okay. If you just want to get into y equals form, you don't really have to solve it past that, I wouldn't imagine. But that is the equation for our tangent line. So the other thing that you need to figure out is, well, there's two things that you could be asked from here. Now that we have our equation, I'm just going to use this just because why not? Now that we have our equation for the tangent line, right? That's the equation for the tangent line. Oh, shoot. What was the original equation? I think it was y equals 3x cubed plus 2x, if I remember. Hold on. So, and then it was x equals 2. Yeah, I think that's right. Okay. So we have our equation, and now we have the equation for our tangent line. So there's two things that could be asked from here. One would be, what is the point at something like x equals 1.9? And that's very simple. All you have to do is you take x equals 1.9 and you plug it into this equation. You do not, and I repeat, do not plug it into this equation. That's a big no, 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 right? You just did all this work to find the equation for the tangent line. All you need is an approximation. So what you're going to do is you're going to do, y minus 28 equals 38 times 1.9 minus 2. Y minus 28 equals 38 times negative 0.1. And then whatever these two multiply together, and then you add the 28 over. I'm not going to do all that arithmetic here, just because that's repetitious and it's not important right now. And then whatever that y value is, that's what the y value approximation is for the tangent line when x equals 1.9. So that's the first thing that you could be asked. Remember, all you have to do is just plug that number back into your tangent line equation, right? The second thing you could be asked is over or under estimation. And what do I mean by over or underestimation? Well, if we have that x equals 1.9, right? And we plugged it into this equation, I have no idea what you would have gotten, but let's say we got 10, right? But the real answer, when we would have plugged that into that equation, this equation, the real equation to get the exact number, let's say it was 10.2. Was the approximation of 10 below, was it an underestimation or an overestimation? Over, greater than the actual 10.2. You see that it's under, right? So that would be an underestimation. Again, I have no idea if it's an under or an overestimation. I'm just trying to explain to you what each of those means. So if you have those two, right? Or now that we know that what those two are, how do we figure that out? Well, what you can do is we can take the derivative of that equation. So y1 equals 9x squared plus 2, right? And then what we can do is we can find what it's called is the second derivative, which is basically just the derivative of the first derivative, right? Because this means first, this means second. The second derivative, so that would be 18x, right? That's our second derivative. So that second derivative is going to be positive when we plug in our x value, right? Right, we plug in our x value and it's going to be positive, so that we know that the slope is opening upwards, and we know that it is going to be an underestimation. So you're probably like, whoa, I just went through that too quick. I'm going to go through it again. So if we know that the second derivative when we plug in x is positive, right? Then the tangent line is going to look something like this. So when we have it under the curve, right? Because if the curve is open, you know what? Let me go through this again. If it's positive, when you plug in the second derivative, the slope opens up, the curve opens up. If it's negative, curve opens down, right? If you have a tangent line of a curve that's sloped upwards, it's going to look something like this. If you have the tangent line of a curve sloped downwards, it's going to look something like this, right? And we'll see that at any point, if the curve it goes upwards, any point on this tangent line, it's going to be an underestimation because all the points are below the curve. So if it opens up, it's going to be an underestimation. So if this number is positive, it's going to be underestimation. If it opens downwards, then we see that any point on the tangent line is going to be above the curve. And we know that it opens downwards if this comes out negative. So then if this comes out negative, this is an overestimation. But again, you plug in the 1.9 or whatever the 2 is, and we see that that comes out positive. So we know that it's a underestimation, okay?